In the last two episodes, we went through the function of our new simulation tool for sustainable power supply, and I gave an example on how to get the resource data for solar and wind energy. Today, I'm so excited to present a realistic example for the electrical energy supply of a household with a small office and, of course, an electric vehicle. From the episode EX06, we understand the principle, the logic, the inputs and the outputs of the tool. In episode EX07, I explained how to get the resources data for solar and wind energy from free sources. And there is a number of interesting examples waiting, which I will cover in several episodes. In this episode, I will demonstrate step by step a typical household with a small office and an electric vehicle, because we are all so curious about that. I want to encourage you to post your ideas for additional examples. Just leave a comment to start the discussion. And yes, the little monster is reminding us to like the video and to subscribe the channel. Here is the summary, which we derived in the last episode from the Global Solar Atlas and from the Global Wind Atlas. In addition to the monthly yield potential for solar and wind, we noted the latitude and the longitude for our location in the Stuttgart region. For our tool, we need the solar panel elevation angle, which is 90 degrees minus the tilt angle. With the given formula, in our example, the optimum elevation angle equals 43 degrees. I hope this is not too confusing. The given tilt angle is between the horizontal plane and the panel, while the elevation angle defined for the tool is between a perpendicular axis to the panel against the horizontal plane. Keep that definition in mind in order to avoid confusion. The optimum azimuth angle for solar panels is 180 degrees, which is exactly the south direction. By the way, the optimum azimuth is always south on the northern hemisphere. On the southern hemisphere it is north, corresponding to 0 degrees azimuth. Of course, in a real scenario, it is not sure that we can realize the optimum angles for our solar panels. But anyway, we can use them to compare our real scenario with the optimum yield we could achieve. We also derived the 7 degrees horizon angle from the Global Solar Atlas. Let's see what we have now and what we need to do next. We have the location-specific yields and the optimum angles. Now, what else do we need for our simulation? We can choose any arbitrary size and orientation for our photovoltaic panels, and we can choose any size of wind generator. Then we need our own consumption profiles for our consumers. We will see in a minute that the tool is giving us a lot of support for this. We start from where we stopped in episode EX07. Then we go to the sheet Generators. In the top section, we fill in the geographical coordinates and the time zone of our location. As mentioned before, for the Stuttgart region, we have 48.77 degrees latitude, 9.18 degrees longitude, and the time zone is UTC plus 1 hour, which is the same for the whole of Middle Europe. Then we can insert the parameters for up to 3 photovoltaic generators, which can have different size and different orientation. Further options are biogas, wind and water generators. Now back to our solar panel number 1. Let's say that panel 1 has an output of 10 kilowatt peak, which corresponds roughly to a panel size of 30 to 40 square meters. For the panel orientation, we use the optimum angles for the moment. This is to demonstrate the logic of the output in the box in the middle section here. When using the optimum angles, the energy from the simulation should be the same as the maximum derived from the resources data. The figure, which I called efficiency, should be about 100% then. We expect that this figure is getting worse the more we deviate from the optimum orientation. Now let's insert the real orientation of our panel 1. Our actual azimuth is 155 degrees, the elevation is 55 degrees, and the horizon angle we found for our location is 7 degrees, as mentioned before. Now the yield derived from our simulation is 93.2% compared to the optimum, which is acceptable. We can achieve this in reality as long as there is no shading of the panels. As we want to make our simulation as realistic as possible, we can insert shading effects that might be caused by chimneys, trees, other buildings, etc. Let's assume we have a broad-leaved tree in front of our house, which is carrying leaves from April to September. For the rest of the year, the tree's shadow effect is only 10% because it has no leaves during that time. We can simulate this by inserting the value 1 to the months April to September, where the tree is carrying leaves. And for the rest of the year, we insert 0.1 corresponding to the 10% shading effect. The duration of the shading is about 1 hour, and it happens at 10 o'clock in the morning. We can consider this by inserting 1 for the 10th hour in the input table. The graphic on the right side shows immediately the effect of the shading. We see here the average power generation of a panel over a day in the middle of each month. And by the way, our efficiency compared to the optimum went down to 80.3%. Now we go to the wind generator. We remember the average wind power density is 95 watts per square meter at our site. With a 4 square meter wind turbine and an efficiency of 30%, our maximum power output at the average wind speed would be 114 watts. 140 watts equals 0.114 kilowatts, which we insert here. Optionally, we can insert a maintenance period during which the turbine doesn't produce energy. Inserting the one in June simulates that effect. Now let's go to the bottom of the sheet, where we get a summary for the energy generation for the year. Our first takeaway from this is Wind turbines of a bearable size cannot bring much contribution to the generation of electrical energy on a private property in Stuttgart. For the moment, we switch it off for the simulation by setting the maximum power to 0. We will come back to this later when we talk about areas with more wind, because it can nicely complement the energy generation, especially during the winter and nighttime. Let's go to the sheet Consumers. This sheet helps a lot to estimate your consumption from the household, from a small office, from air condition or heating, and from an electrical vehicle. I mean, it's rather the exception that you would have your consumption profiles at hand. In case you have smart meters, you might be able to make your estimates more precise. In any case, the estimates you can get with that sheet are a good starting point. We start with the household. The numbers that are populated already are derived from a so-called standard consumption profile for households in Europe. Utilities are using these for their planning as well, but of course you can adapt them to your local information. I introduced some slight improvements to the standard profile. We can differentiate weekends from working days, and we can also insert the standby consumption as a separate value. In case we insert 2 persons living in the household, we get 2644 kilowatt hours yearly consumption, which is the average in Germany. The outputs in the middle section are dedicated to cross-check with your own country standards or your actual consumption in a year. Now we want to represent our actual situation. From January till May, there are 3 persons living in our household. In June, there are 3.5 persons, and in July, there are 4 persons present. In August, we are all absent, and for the rest of the year, there is 3 persons present. We can cross-check the real consumption using the yearly consumption figures in the middle section and the graphics on the right side for plausibility checks. In our small office, there will be 1 person working during the whole year, except in August, where the complete family is absent. We have the typical office consumers, like a personal computer, lights, telephone, etc. The consumption during the working days office hours from 9 AM to 6 PM is 350 watts. On the weekend, it is the same consumption from 7 PM to 9 PM. In addition, there is a network-attached storage server that is always on, and it consumes about 40 watt at an average. Again, we get some aids in the middle section and on the right side to check the plausibility. Now we consider our air condition. Okay, that is again the same logic as before. We insert the active months. In June we need 50% air condition, in July 80%, in August only 20% because we are absent, and in September it is 50%. And the consumption profile during the hours of the day is done according to the intensity that is needed. However, take care, this time it is kilowatts per hour consumption to insert. Last not least, there will be the electric vehicle next year, and we want to know how this would fit to our configuration. Again, we have a similar logic. We assume in our example that we use the car from December to April, only half of the average. In August we are absent, so we don't charge the car at home. Our wallbox can deliver 6 kilowatts and we insert our consumption profile during the week and for the weekend. Our car consumes 22 kilowatt hours per 100 kilometers. This equals then more than 14,000 kilometers per year, which is about the average for cars in Germany. Our monthly consumption overview we found on the bottom. We can use this to cross-check with our real consumptions. Next, we go to the sheet Overview Year. We get here a summary of our monthly and yearly generation and consumption. The total generation over the year is slightly bigger than our total consumption. On the bottom we find the key figures that are important for the economics of our arrangement. Besides the totals, we get the figures for own consumption, main consumption and the feedback to the mains. And there is an indication of the grade of autarky, which is 32.8%. The autarky is slightly better than the average that can be achieved with such a configuration. The reason is that we consume some energy with the air condition during the hot days, and we can charge our electrical vehicle during the day on weekends and in the late afternoon during the week. Our consumption at least is partially synchronized with the generation. For the better understanding of this, we go to the sheet Battery and Analysis. For the analysis, we can choose a day in winter, for example the 1st of January, and a day in summer, for example the 7th of July. Then we get the distribution of energy key figures over the day and the following week. There is a lot of insights you can derive from this, but for the moment we only draw the following resume. During the winter the generation is lower than the consumption, and during the summer the generation is higher than the consumption. Furthermore, the consumption from our electric car is out of sync from the solar power generation during the week. The insights and the summary. Our simulation tool is producing results that are absolutely in line with the experience that we have with solar generators in our region. Since we can simulate partial shading and any arbitrary orientation of the solar panels, it can give you a good estimate whether a configuration that you have in mind makes sense. So far, we covered only a part of the features and only one typical scenario. As mentioned earlier, there is a lot more to come on features and scenarios. We want to simulate other places on Earth, scenarios with wind, water, etc. And we want to simulate buffer batteries and the economy. I think the number of possible applications is almost infinite. And now it is on you to comment and share what you want to have simulated. Now stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.